Welcome back. We're going to take a look in this video at a great search algorithm called binary search. Now, binary search makes use of one property of the list. And if you look at the list I am using in this video, the list is sorted. Now, this is absolutely necessary in order for the logic in this algorithm to work. So it's not cheating, but you'll see what happens when you have a list that's sorted, how fast you can find the values you're looking for. So what I'm going to do here is I'm going to look for the value 30. Okay, and yeah, 30 is in there. So let's just see what happens. Now, the way binary search works is binary search keeps track of a low and a high pointer. So low is set to the smallest index position in the array, 0. And high is set to the highest index position in the array, 15. Now, let's assume our array is called A. A of low, so A of 0 would be 3. And A of high would currently equal 100. Okay, this is the kind of notation you're going to use when you have to go actually write the code for this one. Now, there's a pattern I'm going to follow until my value is found or until my value is not found. Watch for the pattern here, because this is what you're going to be asked to code inside the binary search method. So here we go. Take low, 0, take high, 15, and calculate the midpoint between them. Well, 0 plus 15 is 15, divided by 2 is 7.5. Forget about the half, because we're talking about integers, which would place this variable mid at 7. Now what you do is you go and ask yourself, what's the value at A mid? So A7. Well, the value is 25. And then you now ask yourself 3 questions. Is this value bigger, smaller, or equal to the number you're looking for, 30? So I know 25 is smaller than 30. Well, since it's smaller than 30, there's something you know. I know that that whole part of the list is not going to contain my answer, or sorry, my number 30. So I can sort of ditch it. I don't have to look there. I mean, just the logic of it, right? It's a sorted list. You're here. You know your number's bigger. You're not going to waste time up here. So what do? Well, if your number's bigger than the value at mid, then you change the value of low to be 1 higher than mid. Okay? Now you just repeat the process again and again and again. So let's go for it. Low is 8. High is 15. They add up to 23. Divide by 2, 11.5. Mid would be there at 11. Grab the value at mid, 50. Well, 50 is bigger than my number. That means my number can't be in that area. So what do? I reassign the value of high to be 1 less than mid. So notice when you switch low, you make low bigger than mid by 1. When you switch high, you make it 1 less than mid. You'll probably notice low and high are starting to come together. And each time I move one of them, you are literally ditching half the list. Then this portion of the list, half the list or so gets ditched. This is why this routine is great. Let's keep going. 8 plus 10, 18. Divided by 2, 9. Mid moves up to there. Is my number less, equal to, or bigger than the number stored at slot 9? Well, my number's less, so I know I can ditch those two. This means that I'm moving high to 1 less than mid. Now, this is totally fine. Low and high are now on the same index position, 8. Let's keep going. 8 plus 8 is 16. Divide by 2, 8. Mid now moves there as well. So now we got all of them there. And this is where you basically get close to your finishing point. So you got choices here. The number stored at mid, which is 30, is it less than my number? No. Is it bigger than my number? No. Is it equal to my number? Yes. If it's equal to your number, you return mid. Send back 8. We got our answer. And so that's what you're doing in the loop every single time. You're saying, is my number bigger than mid? Is my number bigger than the value at mid? Is my number lower than the value at mid? Is my number equal to the value at mid? If so, return. Now, if it's not, so let's say the number here wasn't the right number, what would happen next? So I'm just going to change it here and pretend this was like a 29 when I was looking for the 30. Well, it's not. My number is bigger, which means I should be looking higher up the list. What this is going to do in your code is this is actually going to make low go to mid plus 1. Now, by making it go to mid plus 1, what happens now is low is bigger than high. And this is going to be the main condition in your loop that ends your loop. If low ever gets bigger than high, you know that you haven't found your value and your value is not in the list. And that's really the routine, and that's the end point. What would you do if low gets bigger than high? Your main loop of repeating this is done, and you send back -1. And that's binary search. And so there's a lot of good little loop logic there. Get the right loop condition in there. Move low, move high, calculate mid, and you've got yourself a nice little search algorithm. Now, if we talk about the numbers and how efficient this is, you can think about what we just did there. We started with 16 items in the list. How many loops did we have to do? Well, we started with 16. Then we cut the list basically in half. We went down to 8. Then we cut the list down to 4 items or so. Then we cut it to 2 items. Then we cut it to 1 item. So really we did 1, 2, 3, 4 loops to get this to actually find our value or realize our value is not in the list. For those that love their math, this is 2 to the power of 4. So notice we cut in half 4 times, and that would give us 16. 2 to the power of 4 is 16. Using this same logic here, could you predict if you had something like 64 items in the list, how many main loops would you have to do? Well, I know 64 would be 64 to 32 to 16 to 8 to 4 to 2 to 1. This is 2 to the power of, 2 to the power 6. 1, 2, 3, 4, 5, 6. About right. Now, we don't care if you're 1 off here, right? Like 2 to the power 5, 2 to the power 6. But it gives you the idea. This is 4 times bigger a list. Instead of doing 4 loops, I only had to do 2 extra loops, 6 loops to find the value. When you keep applying this logic, you're going to see that if you had 1,000,000 items in the list, well, 2 to the power of something is 1,000,000. And that something is around 20. Okay, it's not exactly 20, but it's 19 or 20 loops. That's not too bad. I mean, this took 6 loops to do 64 number search. By only adding another 14 loops to get to 20 loops, you can now do 1,000,000. And what gets even better is if you had 2,000,000 items, you just added an extra 2,000,000 items to the list. This only requires you to do 1 extra loop. 2 to the power of 21, right? You only have to cut the loop down in half 1 extra time. So you can see that this is very efficient, especially when the lists get huge. But remember, it's not magic. You have to keep the list in order. So if you can figure out how to keep your list in order, whenever you need to do searches, and if you're doing a lot of data searching, like a lot of database programs do, then the binary search, very quick at finding your values. Not too bad, right? Now, how can you actually code this one in? Well, that's what we want you to do, is attempt to code binary search in. So basically, start your low pointer at 0, start your high pointer at the maximum slot in whatever array you're given. Now set up probably a while loop, and the while loop should calculate mid. Check what mid is, compared to the value you're searching for, and you're either going to move the low pointer, you're going to move the high pointer, or you're going to return the index. Maybe that's bang on your value. If not, loop repeats, loop repeats, loop repeats. Keep repeating until you find the value, or until low gets bigger than high. And that's the end point. So we're going to let you try to puzzle that one out. You can go back and use the searching sorting example that we used before. You'll see here, though, you will want to switch your array to a sorted array. And you will also want to switch to using the method binary search. And if it works, and you got to test it a lot of times looking for different values, right? Search for the 3, search for the 100, search for 25, 30, search for all the numbers. Make sure your routine works. And of course, also search for numbers that aren't in there. So you can test if that's working, right? The -1 should come back. So that you can code into binary search here. Good luck with that. It's a great one. If you have trouble, you can go sneak at the little solution video where I'll show you the answer code. Okay, but you should really try to give that one a go. Estimate a time. Sometimes it takes students 5-6 minutes. Sometimes it takes students an hour to do, right? It's not a super hard routine, but definitely if you mess up a tiny bit, the thing just loops forever, right? And just doesn't work. So good luck with that. Maybe plan it on paper first and see what you can do. Thanks for watching.